Good day, students. In this clip, we're going to be going over Lagrange multipliers. We're going to be going over an example on how to find the extrema of a function using the method of Lagrange multipliers. So first thing we're going to do is go over the steps to get the extrema and their classification using the method of Lagrange multipliers. So let's write down the steps first. So step number one. First thing you want to do is you want to identify the function and your constraint equation. Okay, so identify f. It could be a two-variable function or three variables. So whatever it is, just identify f and g equals k. F can be viewed as your objective function, and g equals k can be viewed as your constraint equation. All right. So after identifying them, you're going to set your objective function equal to 0, and you're going to express your constraint equation in the form g minus k, so you can set it to 0 also. All right. So after having this set up, you're going to create a new function. Okay, so let's just call it L. Give it whatever name you want. You create a function L, and it's going to be equal to your objective function f minus a new variable lambda times your objective equation, your constraint equation in the form g minus k. All right. So now when you set up this new function, um, it's going to enable you to set up a system of equations. All right, so you're going to set up a system of equations in step 3. Set up the system using partial derivatives. Okay, so you're going to have the partial derivative of this entire expression, basically the partial derivative of f minus the partial derivative of lambda times g minus k. All right, so remember, when you're looking for the critical points of a function, what you do is you find the derivative and do what? You set it equal to 0, so that's exactly what you're going to do here. When you find all the partial derivatives, you set each one equal to 0. So let's say you're working with a function in 3 variables. What is that going to look like? You have L, the partial derivative of this function with respect to x. You find that, set it equal to 0. That will be your first equation, equation 1. Find the partial derivative of the function with respect to y, set it equal to 0. That will be equation 2. Partial derivative with respect to z, set it equal to 0. That will be equation 3. And then lastly, partial derivative with respect to lambda, set that equal to 0. That will be equation 4. Okay? So this is how it looks like if the function is in 3 variables. If it were 2 variables, you just have x, y, and lambda for your partials, and that will be your system of equations at 3 by 3. All right, so after you solve these equations, what you're going to find are the critical points, okay, or your potential extremas. So after doing this is to find your critical points. Okay, or you can view them as potential extrema. Now, after you find your critical points, how do you classify the extrema as a max or the min? What you do lastly is you're going to evaluate your objective function f, evaluate f at your critical points. The critical points you found for x, y, and z, you're going to plug them into your objective function, which is the original function f. The biggest one is, of course, your max, and then the smallest one is your absolute mean. So evaluate f at your critical points. The critical points and classify them. Okay, classify them accordingly. So classify them as max or min. That's what we're going to be doing in the example I'll be going over today. All right, so let's write down the problem number 1, example 1. you're to find and classify the extrema of the function. We're going to be dealing with a function in three variables today, okay? F of x, y, z equals x plus y plus 2z. This is our objective function. Subject to the constraint. Our constraint is going to be a surface subject to the constraint x squared plus y squared plus z squared equals 3. And of course, you know what kind of surface this is. Alright, so this is what the problem is. Find the extrema and classify them as the max or min. So step 1, we have to identify f in our g equals k constraint equation. So we can see that this f right here is our objective function, and this is g equals k. Okay? Now what we're going to do is we're going to set them equal to 0. So f of x, doing f of x, y, z equals 0. What is that going to look like? Well, we're going to just take this portion of this function, x plus y plus 2z, set it equal to 0. And then next thing we're going to do is we're going to do g of x, y, z minus k equals 0. So basically, set this constraint equation to 0. How do we accomplish that? Simply subtract 3 from both sides, okay? So you're going to have x squared plus y squared plus z squared minus 3 equals 0. So there you have your two equations. Now what does this help us do? In step number 2, we are going to be creating a new function, right? The L function. So L of x, y, z, and the new variable lambda is going to be basically, let's write down the formula to guide our construction. To generate the L function, you're just going to do f minus lambda times g minus k, okay, which is the constraint equation set equal to 0. So let's go ahead and do that. So f is this expression right here, x plus y plus 2z, right, minus lambda times g minus k is this expression right here. So x squared plus y squared plus z squared minus 3. Okay, so this is our new function, our L function. Now this L function is what we're going to use to set up our system of equations. Okay, so what we're going to do now is basically do the gradient, the partial derivative of L, which is going to be the partial derivative of f minus the partial derivative of lambda g minus k. We're going to find that, and we're going to set each partial to 0. Okay, so that's what we're going to be doing now. All right, so first we're going to start with x. What we're going to do with x, we're going to find the partial derivative of function L with respect to x, set that equal to 0. Okay, so what is that going to look like? So differentiate this piece, the objective function piece. If you differentiate that with respect to x, everything else is a constant, so they drop to 0. Derivative of x is 1, so we have 1 minus, differentiate x squared, you have 2x times negative lambda minus 2x lambda. And then remember, we are setting it equal to 0. Okay, so the partial equals 0. That's how we set up our system. So that's equation 1 for you. To get equation 2, we'll find the partial of L with respect to y and set that equal to 0. So similar to x, so we can just follow the pattern. 1 minus 2y lambda equals 0. And next, L, differentiate L, the partial derivative of L with respect to Z, set that equal to 0. Z, you have a 2 here, so let's be careful with that. Slight change, we have 2 minus 2z lambda, set that equal to 0 also. All right, we need one more equation to set for our system of equations, which is the partial of L with respect to lambda. Okay, so if we do that, we're going to have, this has no lambda in it, so it drops to 0. And we're going to have negative, because derivative of lambda is 1, we're going to have to put the 1 there. 1 times the constant that's being multiplied by lambda, which is x squared plus y squared plus z squared minus 3. What do we do with that? We set it equal to 0. So this is our system of equations that we're going to use to find the critical points. All right. So this is how you go about doing it. Look at equation 1, 2, and 3, and then you solve them in terms of x, y, and z. So equation 1, you get x isolated. You solve equation 2 for y, solve equation 3 for z, and their values are going to be in terms of just lambda. You plug in those 3 answers into equation 4. That will help you find the value of lambda. And then you're going to plug them back into each equation to find x, y, and z. All right. So step 1, in solving this system, let's solve this equation 1 for x. So to do that, we would just subtract 1 from both sides and divide by -2 lambda. So we're going to have x is equal to 1 over 2 lambda. All right. And then this second equation, solve for y. Subtract 1 divided by -2. You end up with 1 over 2 lambda also. And then you solve this equation for z. This one's slightly different because of this 2 here. So you move 2 over -2 divided by -2 lambda. This one you just have 1 over lambda as your value of z. Okay? Now what we're going to do next is we're going to substitute these 3 values into equation 4. Okay? So we substitute them into equation 4. That will help us find out the value of lambda. Let's go ahead and do that. Before I do that, you see this minus right here? I can divide both sides of my equation by -1. So I'll have x squared plus y squared plus z squared minus 3 equals 0. Now if you pause for a second, do you recognize this equation right here? Absolutely. This equation is the constraint equation set to 0, right? So that's basically what the partial respect of lambda does. It just basically generates the constraint equation when you set it equal to 0. So that's the rule of the last partial that we did. Okay, so let's plug in these values. We're going to have 1 over 2 lambda square. When we substitute the value of x into this last equation. Same story for y. 1 over 2 lambda square. Z is 1 over lambda, so 1 over lambda square minus 3 equals 0. Okay, so let's go ahead and work this out. I'm going to work this problem out. We're going to have 1 over 4 lambda square plus 1 over 4 lambda square plus 1 over lambda square minus, well, we can set this equal to 3, add 3 to both sides, so we can get lambda isolated, okay, equals 3. Now we can just find the LCD of these 3 terms. This one doesn't have a 4, so you can just introduce a 4 here. All right, and then you combine it all together. You're going to have 6 over 4 lambda square equals 3 over 1. And then you can just cross multiply. You have 6 over 12 equals lambda square. And then when you read both sides, you have lambda equals plus or minus the square root of 1 over 2. When you reduce 6 over 12, you get 1 over 2. So this is basically plus or minus 1 over root 2. All right, so it looks like we're going to be having two critical points here. One where lambda is negative 1 over root 2, and then the second one is where lambda is positive 1 over root 2. Okay, so let's go ahead and find out what x, y, and z are. Let's rewrite the values equations for x, y, and z. Remember, x is 1 over 2 lambda. Y is the same story, 1 over 2 lambda. And z is 1 over lambda. Okay, so let's find our critical points. So when lambda is equal to negative 1 over root 2, we're going to have x is going to be 1 over 2 times negative 1 over root 2, right? And then when we simplify that, we're going to have simply going to be negative root 2 over 2. We multiply top and bottom by negative, you just multiply by root 2 over 1, top and bottom. You get this. Same story for y. Substitute that 1 over 2 times negative 1 over root 2. Y is going to be negative root 2 over 2. And then when you plug in 1 over negative root 2 for z, 1 over negative 1 over root 2, that's simply going to tell us that z is negative root 2. Okay, so our first critical point is the order triple, negative root 2 over 2, negative root 2 over 2, and negative root 2. All right, the second one we're going to find is when x is equal to when lambda is equal to positive 1 over root 2. So let's go ahead and find that one out. So when lambda is equal to 1 over root 2, what do you think is going to happen? All that happens is the signs just change. Okay, same procedure, but the signs change. So we can see that when x is 1 over root 2, when lambda is 1 over root 2, x is going to be root 2 over 2, y is going to be same thing, root 2 over 2, and z is going to be the opposite of that, which is root 2. So our second critical point is root 2 over 2, root 2 over 2, and root 2. So now the question is which of this is the max and which is the min? Okay, how can we classify them? Remember the last step, you evaluate your critical points. You evaluate your original objective function f at your critical points. Okay, so we're going to plug in the answers that we just got into the objective function f, because remember, we're looking for the extrema of this function, okay, subject to this constraint. So that's what we're going to plug it into. So it's pretty straightforward to do that. We're going to do f of negative root 2 over 2, negative root 2 over 2, and negative root 2. So you're just going to plug in these values into your objective function. All right, so let me just write down the function that we're plugging it into up here so I don't get confused. The function f, put this over here. So we have f of x, y, z. All we're simply doing is we're going to do x plus y plus 2z. Okay. So just plug it in. We're going to have negative root 2 over 2 minus, times plus is minus, root 2 over 2 plus 2 plus times a minus is a minus. So it becomes minus 2 root 2. Okay, so put this over 1 and then find the LCD. Just times it by 2 top and bottom. So this becomes 4. So you have 1, 1, and 4. That makes 6. So that this becomes negative 6 root 2 over 2, which reduces to negative 3 root 2. All right, so that was a value at this critical point. And the next thing we want to find is f of root 2 over 2, the second critical point, actually the first one, root 2 over 2 and root 2. Same story, root 2 over 2 plus root 2 over 2 plus double that to root 2. Put this over 1, find the LCD. And then what do we have here? We're going to have 1 plus 1 plus 4, which is 6. 6 root 2 over 2, which reduces to 3 root 2. So we have our extrema at these 2 points, and then this is the max, this is our minimum, and this right here is our maximum. Okay, so let's see. All right, so let's write down a sentence to just summarize what we just found to make sure we're answering the question. So we have the extrema of the function, the extrema of f are at, where are they at? They are at negative root 2 over 2, negative root 2 over 2, negative root 2, and root 2 over 2, root 2 over 2, and root 2. And then we have a maximum of 3 root 2, and a minimum at a minimum of negative 3 root 2. Okay, so that's basically that. So thanks so much for taking the time to watch this presentation. Feel free to subscribe to our channel for other cool clips such as this. And do post a comment to let us know what you think about this presentation. We really appreciate it. More clips can be found on mathlearnserve.com/calculus. Thanks again for watching and have a wonderful day.